Okay, this is Unit 3, Video 2, net force. Okay, and so we did the first lecture on Newton's first law, inertia, in class, and then we did the second and third law in the last video. And so this video is going to talk about net force. We're going to talk about free body diagrams, which you're going to learn how to draw today. We're going to use free body diagrams to solve for net forces, and we're going to calculate static and kinetic friction using the normal force. All right, so before we really get started, I want you to just sort of remember the second and third law. So remember the second law was F equals ma, okay? And we're actually going to make a teeny tiny adjustment to that today. And then the third law was action-reaction forces. All right, so for every force, there's an equal and opposite force, so that was the third law. All right, so as we get into this one we're going to talk about net force. And the way that I kind of want to introduce this is by using money, just because I think we understand that a little bit better. So this first part says, what is the difference between gross and net income? So if you make $100 per day, but then you pay $30 in taxes, $5 in gas, and $3 in lunch each day, then what would be your net income, right? And so I think this is pretty easy to figure out, right? We have $100 given to us, but then we pay out 30, we pay out another 5, and we pay out another 3. So if we take those away from 100, it's really 100 minus 38. And so we should get a net income of, what is that, $62? $62. So you took the amount that you were paid, the positive amount you were paid, and you basically took away all the negative parts, the negative payments, the things you had to push out. And that would give you your net income. This 100 is your gross income, right? And the net income is the difference of the positive that you got paid to what you're paying out. Now that's the exact same thing with forces. In order to find the net force, you're going to hear this word a lot, you take the positive forces and you just subtract the negative forces. The positive forces are the ones that are up or to the right. Negative forces are down or left. Okay, just the direction. And the adjustment I kind of want to make on this equation is that really that second equation should say net force equals ma. So we will be dealing with the net force more at this point, okay, and just F net, all right? Okay. All right, now a free body diagram is a drawing of a single object with arrows representing forces acting on the object. Now, this is the thing that gets really confusing for people is for some reason you guys are going to want to draw the forces that the object is exerting, but that's not what the point is. The free body diagrams are the object and the forces that are on that object. So we'll do some examples and you'll be able to see what I mean by that. The arrows always come out of the box. I like them to come out of the center of the box, so draw that when we do it. The direction obviously matters. That's the direction of the force. And the size of the arrow is the magnitude of the force. So how big is the force, basically, okay, or how strong. All right, we have a few equations here. Let me see if I can get this to focus. Okay, we have a few equations. Okay, we have F net equals ma net. The net on the A, to me, it's kind of a waste. It's just the acceleration, the net acceleration is just the overall acceleration of the object. So I kind of don't like that net on there, but if you want to keep it there, that's really technically the right equation. F net, right, is what we talked about up here. F net in the x direction is equal to the forces from the right, forces to the right minus the forces to the left. And the F net in the y direction is the forces up minus the forces down, right? So positives minus negatives, positives minus negatives. And yes, the x and the y have to be separated. That's what this says. You must combine horizontal or x forces separately than you combine vertical forces. Okay, so you never do an F net where you're combining an up force with a left force. Okay. All right, so let's draw some free body diagrams. So FBD is short version of free body diagram. Okay. So draw an FBD or free body diagram of a skydiver without air resistance and one with air resistance and at terminal velocity. So let's make this guy the one without. Okay, so this guy is without. All right. Now, if he's without air resistance, that means the only force on him is the force of gravity. So from the center, we draw down and we label it FG, force of gravity. Okay? Since there's no air resistance, nothing's pushing him up or right or left. So that's the free body diagram. We're done. In box 2, be sure to label all forces as one of the 5 forces described in class. Okay, so that's fine. We already did that. So this guy now has air resistance and they're at a terminal velocity, meaning that they are no longer accelerating. So what that means is that the force of gravity that pulls down has to be equal to the force of air that pushes up. So the length of these two should be equal, okay, so that it looks balanced. So you can always represent the object with a little box rather than drawing the object. It's kind of hard to always draw the object. It just takes a long time. If you really like drawing the object, that's fine, but boxes work for me and that's what I'm going to use. And then whenever you're describing a force, you want to make sure you use like FG for force of gravity, F, what else did we talk about? Probably like F, friction, so FF, right? If it's a thing that is like the air or a push or a pull or anything like that, you can just put F air, F push, F pull, okay? So just, you can kind of name it whatever you want to describe what that force is, but make sure you know what that force is, don't just put F. All right, number 2. Draw a free body diagram of a car traveling at a constant speed, so that's key. That means that the forces are all balanced because there's no acceleration. And one of a car accelerating from rest, assuming that there is a small amount of friction. Be sure to label all forces. Okay, so the first one we're going to say constant speed, so there would be some force pushing it to the right. Let's say that's the engine. Okay. And then there would be friction acting backward, and these should be equal length since the car is going at a constant speed. So this would be the force of friction. Okay. And then one accelerating from rest, so the friction is small, so the engine force is nice and big, and the friction force is small. And so you can see by the picture that this one is not accelerating and this one is accelerating, and it's accelerating to the right. So the pictures really show you a lot. Okay, you have to draw these pictures for every single problem now. All right, number 3, a 500 kilogram car's engine produces 2,000 newtons of force. So mass equals 500 kilograms. Force of the engine equals 2,000. And it experiences a force of friction of 500. Draw a free body diagram. So, okay, there's the car. We have the engine force. Since it didn't specify, you can pick what direction it's going. I'm going to just say it's going to the right. So engine force that way. Friction force this way. And I'm going to actually put the numbers. Okay. And then it says to make a horizontal and vertical F-net equation and solve for both. So this is a car, and actually we forgot on this one, both of these, that there is a force of gravity on these cars, right? And there's also a normal force, which I can't remember if we talked about that yet, but if we didn't, then we're going to talk about it in a minute. Okay, so a normal force on each of these. And the force of gravity and the normal force should be balanced so that it's not accelerating up or down. And we kind of forgot about that on this one as well. Okay. So horizontal net force equation, so F net in the X, okay, equals the forces to the right, so the engine, minus the forces to the left, so the friction. So if we do that, we get 2,000 minus 500, and we get that the F net in the X is equal to 1,500 newtons. Okay. And then in the y, it would be the normal force, because that one's up, minus the gravity force, that one's down. And we do know the gravity because we have the mass. So we know the gravity, let's see, so solve this over here. Force of gravity is mass times gravity, acceleration of gravity. So it's 500 times 9.8. If you made it negative, that's fine because it's going down. Okay, and since these are balanced, we know this one has to be 4,900 newtons up. Okay, so this will be 4,900 minus 4,900, and we should get 0 newtons in the y direction, since it's not accelerating in the y direction. Oops, sorry. Okay, so hopefully that makes sense. All right, and let's go ahead and move to the next page. All right, so we've actually not done normal force, it looks like. So we will do that now. Okay. All right, so the normal force is basically the force of any surface pushing up on any object, or I guess it doesn't have to push up, it could push in any direction, but most of the time it pushes up. So right now my calculator is sitting on my desk, and there is a force of gravity on my calculator. Obviously it has weight, so gravity is pulling it down. And the reason it doesn't fall through the table is because the table is exerting a force back up on the calculator in the perpendicular direction, so straight back up. And that force is called the normal force, okay? So like this little, whatever the heck this is, little elf, is standing on some surface. And so the forces on that elf would be the force of gravity, and then it would also have a normal force pushing up. And those need to be equal. Otherwise, this elf is either going to fall through if the gravity is too big and the normal force can't support him, or he's going to accelerate up if for some reason the surface could push him up. That wouldn't make any sense, okay? But anytime you are sitting, like right now you're probably sitting in a chair, and the chair is pushing up on you, matching your weight in order to keep you from falling through the chair, okay? It's how hard a surface is pushing upward. The normal force always acts perpendicular to the surface, all right? So if you had like a ramp and you had a box sitting on a ramp, and we may have already gone over this, the normal force pushes perpendicular to the surface, even though gravity is pulling this box downward, okay? So this would be the normal, and this would be the gravity, all right? All right, friction. I think we talked about friction already a little bit, but friction is just sort of the resistance of a surface that's going against the motion, resist motion. So a person's friction can be affected by how hard the ground is pushing up. So the equation for friction is the normal force times, oops, I wrote this wrong. Do this in this order. It's this weird M looking thing times the normal force. That weird M thing is called mu. It's called mu. It's a Greek symbol. The way that I learned how to draw it is it's basically like an M, but without finishing the other side. Okay, so you'll get used to it, or it's a U with like a really long front piece. I don't know. But it's called mu, okay? The units for force of friction would be newtons. Obviously, it's a force, okay? Now, mu is just a coefficient of friction, and it has no units. Mu is basically like how rough is a surface. So the mu will be bigger if the surface is rough, and it'd be smaller if the surface is smooth. So like ice will have a very, very low mu, but sandpaper would have a really, really high mu. And basically mu is like, it's usually a very small number. It's like somewhere between like 0 and maybe like 1.5. It's usually not much bigger than that. Usually it's below 1. It's usually a decimal, okay? Now there are two different types of friction. There's static friction and there's kinetic friction. Static friction is when an object is at rest. Kinetic friction is when an object is sliding. So static friction is like when you try and push a couch on a carpet, and the first push that you're trying to get the couch moving is really difficult to try to get it just to slide. But then once it's sliding, it's like not as bad. And that's because the static friction, trying to get it to move, is actually bigger. So static friction is always greater than kinetic friction. Kinetic friction is always less. It's always easier to slide something than to get it moving from rest. And that's really just because of inertia, okay? But static friction is when an object is at rest and we're pushing it. As soon as that object starts moving, kinetic friction kicks in. So we're going to do some examples, but that gets a little bit weird. If you're doing static friction, then you would just want to label it like this, mu equals mu static times the normal force. And then if it was kinetic, you would just label it mu kinetic times the normal force. So each object will have a different mu for static than for kinetic, okay, because this one will always be bigger than this one. You can see based on this equation that friction is based on how hard an object is pushing down on a surface and how hard that surface is then pushing back on the object. So the heavier an object, the more force of gravity that object has on a surface, the surface is going to push back harder, and it's actually going to make the friction bigger. Okay, and we'll do some like little examples in class about that to show you. All right, so let's go through some examples here. So I put some problem solving steps on the side. First step is always a free body diagram. Second step is always an FNet equation, and the third step is always substitution into an equation. Okay, and we don't have that many equations, so it shouldn't be too difficult to decide. All right, so example 4, a sled of mass 50 kilograms is pulled. I'm going to just list my variables here. Pulled along a snow-covered flat ground, the static friction coefficient, so mu static, is 0.3. There's no units on mu. And the sliding friction coefficient, so mu k, is 0.1. What is the force of gravity of the sled? So force of gravity, we know, is equal to m times acceleration of gravity. So 50 times negative 9.8. Oops, let's put units on that. Okay, negative 490. What force is needed to start the sled moving? So here's where it gets a little tricky. Let's draw ourselves a little free body diagram here. Okay. This is some pushing force to get the sled moving. Okay. We have gravity, which is 490. You could put negative if you want. We have normal force, which, since the box or the sled is not going to move up or down, it's not going to accelerate that way, we know this has to be 490 also. And then we have, right now, we have friction. We have static friction right now, but friction, okay? So in order for this to get moving, the pushing force has to be bigger than the friction force. And since it's not moving, the friction force is static friction, okay? So basically, in order to get it moving, F push has to be bigger than static friction. So we need to find out what is the static friction, and that's the amount that we would need to push with, okay? So static friction equals mu s, which we have is 0.3, times normal force, which we already figured out in our free body diagram, is 490. And so that friction is 147 newtons. So if we want to start it moving, we need to push with at least 147 newtons. So we can just box that. Don't change it to like 147.1 because technically 147.000001 would also work. So just 147 is fine. That's the force, that very least amount of force we would need to start it moving, okay? All right, we already drew this, so that's fine. Draw free body diagram and then complete the rest. What force is needed to keep the sled moving at a constant velocity? So now we're assuming it's moving, okay? And the free body diagram doesn't change. It's just that now we're assuming that it's moving, so the force of friction changes. So to keep it moving at a constant velocity, whoops, that would mean that the force of friction would be equal to the pushing force. in order to keep it moving at a constant velocity. Because if they're not equal, then it's accelerating. Okay? So now we're talking about it moving, so we need the force of friction kinetic. So this is mu k times the normal force. So in this case, it's going to be 0.1 times 490. And that will give us 49 newtons. Okay? If we don't push with 49 newtons, it will slow down because of friction, because the friction will be bigger than the pushing force. Right? All right. Once moving, what total force must be applied to the sled to accelerate it 3 meters per second squared? Okay, so the applied force is the push force to make it accelerate. So it's going to accelerate in the x direction. So we're dealing with these forces. Whoops, can't see that. Go back up here. Okay, we're dealing with these forces because we're in the x direction. So F net equals ma. Okay, but then the net force is also solved by figuring out the positive forces minus the negative forces. So with the push force minus the friction force equals ma. Okay, so we're going to use this equation. So the pushing force minus the friction force has to equal ma, and we have to plug in what we know. So we're trying to find the pushing force that's necessary. If it's moving, then we know it's kinetic friction, so we know that this number is 49. The mass is 50, and it wants to accelerate at 3. So now we just do the math and we solve. So F push is 150 plus 49, so it'd be 199 newtons in order to accelerate the sled at that rate, at 3 meters per second squared. Okay. All right, last problem here. Example 5. A lawnmower with a mass of 25 kilograms, so I'm going to write that down, being pushed across the yard. The coefficient of friction between the mower and the ground, I'm assuming it's moving, is 0.2. What force is needed to keep the mower moving at a constant speed? So it's moving, so same idea, okay. We've got a push force, we've got a friction force, we've got gravity, we've got normal force. Gravity is equal to mass times acceleration of gravity, so 25 times negative 9.8. So I know that gravity force is negative 245 newtons, which means that normal force has to be 245 also, because it's not accelerating up or down. And then I'm trying to figure out what this force needs to be to keep it moving at a constant speed. And if it's moving at a constant speed, then these two must be equal. So this force of friction is what I need to find in order to find the pushing force. Because I know the push force would equal the friction force, which equals mu times the normal force. It's the equation for friction. So the push force of the friction force is equal to 0.2 times 245. So I get 49 again. So the pushing force has to be at least 49. Actually, it has to be exactly 49. Because if it's bigger than 49, if that number is bigger than 49, then it's going to accelerate this way. If it's smaller than 49, then it's going to slow down because friction will be bigger. Okay? And then what force is needed to accelerate the motor at a rate of 2 meters per second squared? So same idea as this part, right? If we want to accelerate it, that means that we have a net force equal to ma. The net force is also the positives minus the negatives, so the push minus the friction equals ma. The push we don't know, that's what we're looking for. Friction is 49, m is 25, a is 2. So this is 50 plus 49, so the push must be 99 newtons. Okay, so that's sort of how that works. And we will go ahead and talk more about this. I do want to point out one other thing. The static friction. So remember how I said if the pushing force is bigger than the kinetic friction while it's moving, then it will slow down. But if the static friction is bigger than the pushing force, it's not going to move at all. Okay? And so we'll talk more about the static friction because it's kind of a weird thing, but we'll talk more about it in class. But for now, you just need to know that if the pushing force is less than the static force, then it just won't start moving, right? So it has to, basically, the pushing force needs to get bigger than the static friction in order to get the object to start moving. And then once it moves, it no longer is static friction, now it's kinetic friction. Okay? All right, I know that was a long one, sorry.